So, we have been discussing about vibrations of membranes in the present lectures. So, today we are going to look at the vibrations of a circular membrane. So, we have in the previous lecture looked at the rectangular membrane. So, today we are going to look at a different geometry, which is the circular geometry. So, consider this as a circular membrane. We are going to consider a membrane with fixed edge. So, the radius of the membrane, let it be small a, any point on this membrane is denoted using the coordinates r and the angular coordinate phi. So, using this and our field variable, which is the displacement of the membrane from its equilibrium position measured at a coordinate location r comma phi at time t. So, this is the transverse displacement of a point at r phi at time t. So, the equation of motion. So, if mu is the areal density, and T is the force per unit length, so in the polar coordinates, so the Laplacian operator along with the boundary condition. So, the displacement on the boundary is 0. So, we will be looking at the modal solutions of this of the circular membrane. So, we are interested in solutions of the form of this structure. So, if I substitute this solution in the equation of motion and in the boundary condition, and I do a rearrangement by removing this exponential I omega t, so this along with the boundary condition So, then this defines our eigenvalue problem. So, this is our eigenvalue problem, which we must solve in order to determine the circular natural frequencies and the modes of vibration of a circular membrane. So, we search for separable solutions. Once again, as we did for the rectangular membrane, we look for solutions which are separable in r and phi. And this is motivated by the fact that these are independent coordinates. So, they can be separated out. So, if we are searching for solutions with this structure. So, let us see what happens when we substitute this in here. So, let me indicate del r with the prime and derivative with respect to phi with dots. So, here I have used del r by prime and dot indicates del phi. Now, I do some rearrangements. I divide this throughout by this product r into phi. So, then now, you see that this capital R is only a function of the coordinate r, while phi is only a function of the coordinate phi. So, if this which is a function of r and this which is purely a function of phi. So, and that must add up with a constant which is independent of r and phi, and that if has to be equal to 0 for any r and any phi, then it is natural that these are all constants. So, which means I will write it as minus of nu square for reasons that will be clear later. Since I want, you see that this is going to give me this equal to 0. So, the this is purely a function of the angular coordinate phi, and we must have periodicity in this function, otherwise at phi equal to 0 and phi equal to 2 pi, this function will not match. So, we must have now that can be ensured when phi is proportional to an exponential I m phi, where m can be zero, plus or minus 1, plus or minus 2, etc. So, we must have essentially what this means is we must have solutions in terms of cos m phi and sin m phi. So, that can be written in this complex form. Now, this solution is possible only if I choose this constant to be minus of nu square, and nu cannot be now arbitrary. We know that nu has to be an integer, so that this periodicity condition is satisfied. Now, if you have this as minus m square, so I can write, so this equation then becomes, can be written as let me define this as gamma square, and this is minus of m square, so that must be 0, where gamma is omega over c. So, this is the equation governing our radial function. So, this equation was for the angular function phi. So, this is for the radial function r. So, for the angular function we must have solution like this. So, our solution till now what we have is like this. So, this function. Okay, now we have to solve for this radial function. Now, this has in addition the boundary condition. So, if you use the boundary conditions, then you have r at the periphery of the membrane at r equal to a must be equal to 0. So, this equation has to be solved with this as the boundary condition. Now, this is a second order ordinary differential equation, but we have only one boundary condition. So, let us see what happens, because this is going to lead us to something interesting. Now, this equation, this differential equation is known as the Bessel differential equation. And we have come across this differential equation when we discussed the hanging string. If you recall, there also we had the Bessel differential equation, except that this term was 0. So, let us see, then we can draw an analogy from the hanging string, and you can understand why only this one boundary condition will suffice. The other condition comes from the finiteness of the solution. So, let us see what is the solution of the Bessel differential equation. So, the solution of the Bessel differential equation. So, this is a very standard differential equation in mathematics, and the solution can be written as some constant in this form here. So, this is called the they are the Bessel's function of first and so these are of order m, Bessel functions. This is the first kind and this is the second kind, and they are of order m. Now, since we have the solution as a linear combination of these two functions, let us once have a look to just have an idea of these functions. So, this figure shows the Bessel function of first kind. Here I have plotted only the 0th order Bessel's functions, j 0 and y 0 as a function of this argument s. So, here actually for integral values of the order, this Bessel function of the second kind has a logarithmic singularity at argument equal to 0. So, this is known from theory of Bessel functions. So, what this means for our membrane is that at r equal to 0, this function is going to introduce a logarithmic singularity. That means, this is going to go to minus infinity, which we do not want. I mean, physically we do not have this kind of a behavior. So, we must drop this function from our solution. Bessel functions of all order of second kind, they have this kind of a singularity. So, we must write our solution or express our solution only in terms of the Bessel function of the first kind. Now, if you do that, now we have just one boundary condition. So, R A is equal to 0, and that implies so we must so A is the radius of the membrane. So, we must choose gamma. Now, remember that gamma is omega over c. So, we must choose these gammas so that this condition is satisfied. Now, let us look once again at the Bessel function of the first kind. Let us say with m equal to 0. So, 0th order. So, this function goes to 0 at these points. So, in this figure there are only 3 visible, but then this function has infinitely many roots. So, this goes on and on. So, the first 3 values of gamma times A, which are now indexed with m and the root number. So, this takes a number 1, this is the second root, this is the third root. So, 1 is 2.405. So, this is approximately that 2.405, this is 5.52, and the third root is 8.654. So, the first 3 solutions of this condition therefore are obtained here. So, therefore, our frequencies also now get indexed. Let me first write this in this form. So, so this is gamma mn times c. Now, gamma mn, let us say omega 0 1, as we have seen, is 2.405 over A times C. So, that is the circular eigen frequency corresponding to the mode 0 1, and in this way you can determine the higher modes. So, here I have listed out the some of the higher modes as well. So, these are with m equal to 0, these 3 what we have seen, and this is with m equal to 1. So, 1 the first root, with 1 the second root, etc., and therefore, the circular eigen frequency or natural frequency of the circular membrane is given in this form. So, let us once again have a look therefore. So, our solution was in this form. Now, when m equal to 0, so when m is equal to 0, we have what are known as the axisymmetric modes. And for m not equal to 0, we have the unsymmetric modes. Now, let us look at, and so finding these roots of the Bessel so this is essentially finding roots of the Bessel functions of the first kind. Now, finding these roots is actually a little cumbersome, though in various softwares or numerical analysis programs these are coded.